Hello, everyone. Come on in. Hope everybody had a great break. Hope my internet connection is not as slow as it seems to be, and seems to have been all day today with my phone going quite slow, and now my computer taking forever to even come on. Send me post a comment if you're not hearing my voice. Maybe you're just seeing my lips move. I know y'all can't hear that if that volume's fine. Thank you, Makita. Awesome. Anybody have any questions before we get started? We're going into chapter 29 today, which is called Electromagnetic, Induction, and Faraday's Law. So we're getting yet another one of Maxwell's 4 equations. I was afraid that was happening, Gerald. I think the internet is running really, really slowly. I don't have anything else on in my house that's running the internet. I've even got my, let me make sure, I think I got all my apps shut down on my phone too. Well, I do now at least. I got plenty of Wi-Fi bars. I know that's not the problem. So the video is lagging. I'm going to try to teach anyways. If it looks like it's getting too bad, I will complete the lecture without internet. And that way it won't have any jerks in it because it's recording locally instead of in the cloud. And then I'll post it tonight on my YouTube channel. So if you're subscribed, of course, as soon as I post something, it'll tell you. I definitely recommend, again, you guys being subscribed to my YouTube channel. You can get rid of it when the class is over, but at least that way you always know when I post something new. So does anyone have any questions? All right, well, I reminded myself by writing it on my sheet. So let me turn on my document cam. So today's the 14th of March. And what I want to remind you of is that we have already finished chapters 27 and 28. We're starting on 29 now. So I've made the test available, test 4, and that'll be due Sunday. So it's just another online test. But it gives you, like I said, the practice test has been up for 2 weeks, I think. And now the actual test is up as well. So try to get that done before 11:59 on Sunday. Looks like everybody's here that's coming. So don't forget that, everyone. Test 4, chapters 27 and 28. Of course, they're always comprehensive, but chapters 27 and 28 will be the largest part of the focus. And it's due Sunday at 11:59 p.m. I believe that's the 20th. So what I thought I'd first talk about, and this hopefully, let me know by typing if you're not able to follow me because I am too glitchy or something. But this chapter is on induction, and induction is what allows us to do a lot of neat things that you're probably seeing for the first time. For instance, I have an Apple Watch, and I can just lay it on this little disc and it charges it. And I have an iPhone and I can just lay it on a charger, just lay it on there. I don't have to plug it in or anything, and it charges. That's all induction. Okay, that's the stuff that we're using, and we're getting ready to talk about it now. If you've ever seen a stovetop where you can actually be boiling water, move the pot of boiling water, and then it'll immediately lay your hand on the stovetop, that's called an induction stovetop. And that does the same thing. Basically, you're setting up currents, say circular currents usually, in the stovetop like this. That's actually inducing the current in the pan. And then that pan is, of course, because it's not that good of a conductor of electricity, tends to heat up, and that heating up is actually doing the cooking. So that's some of the things that we're just now beginning to see, and that's because of induction. And really what made it sort of feasible and applicable nowadays is basically the cheapness of chips and things of that sort. So we can basically do a lot of things that used to take a lot of small parts, people soldering together and stuff like that. Now we have complete integrated chips where literally you can have a chip that's this long that's a full wave bridge rectifying variable voltage source. So there's all these little neat little things you can buy. You just, if you're an electrical engineer, you've got catalogs of them, and they sort of run the show, and they're dirt cheap and stuff like that. So that's kind of neat. So that's what we're going to learn about today. And the way I can get you to see it yourself, and the way you've probably already seen it yourself, is in high school or elementary school or middle school, you probably took a nail and wrapped wire around it. Okay, when you take a wire and wrap it around a piece of metal, and then you run a current through it, that actually makes a magnetic field. And if the for instance, the nail is longer than the loops of wire, that magnetic field goes all the way out to the end of the nail. If the nail is not too long, of course, if the nail is like 18 inches long and you only got 3 inches of wire, it might not stay in that whole length, but it's still going to stay in a good distance. But here's the weird thing. If I then stuck another coil of wire over here by the end of the nail, so we've got the coil of wire around the nail like this. This is the end of the nail head sticking out. I've got another coil of wire here. If I move that coil onto that nail, or if I move that nail into that coil, I will actually create a current in that coil, even though there's no kind of battery or anything in it at all. That's induction. What's going on is you usually take a changing magnetic field, specifically a changing magnetic flux. We've learned about electric flux. Now we're going to treat magnetic flux. When you have a changing magnetic flux, that actually creates an electric field, and it creates an electric field that's perpendicular to the sort of current that would produce the magnetic field that's changing. Okay, so you have to have the flux changing, and remember, flux is made up of two things. We did it in Gauss's law. It was the closed integral of E dot dA. Now in Faraday's law, it's going to be the integral of B as in magnetic field dot dA. So you can change the magnetic field flux by changing the magnitude of the magnetic field, changing the direction of the magnetic field, changing the magnitude of the area, or changing the orientation of the area with respect to the magnetic field. All those are different ways you can change the flux. But when you change that flux, you actually create an electric field that's able to drive a current, and that is induction. So you've already made sort of an induction device, or at least half of an induction device, just by making an electromagnet. All you had to do to see the inductive properties of it was to bring another coil of wire, say with a galvanometer on it, near it, and you'd see that immediately once it changes near the electromagnet, it will actually create a current, but it only does it while it's changing. So if I actually take the coil here and I stab the nail in it and then just sit it still, the current stops. There's no current going anymore at all because there's no changing of the magnetic flux. But when you start to pull it out, it creates a current again, and there's a very specific direction in which that goes, and that's part of what we call Lenz's law, which basically says the magnetic flux, the change in magnetic flux creates a current in a direction to oppose the change in flux. It doesn't oppose the flux, it opposes the change in flux, okay? So if the flux is decreasing, it tries to increase that flux. If the flux is decreasing, it tries to increase that flux. So I think I said the same thing twice, but anyways, if the flux is increasing, it tries to decrease it. If the flux is decreasing, it tries to increase it, okay? So that will allow you to solve a lot of neat little problems. A demonstration I wish I could do right now, but since I'm at home, I can't, and I have it in my lab. But basically, I took a coil of wire, and in fact, you can just buy a spool of wire if you wanted to. Then you ain't got a coil; it's already coiled, and you grab the two ends if you can find them. That's the hard part. Okay, you grab those two ends and you solder them, say, to an itty bitty light bulb. There's a very special kind of bulb. It's really hard to get now. I go around on eBay and buy wherever I can find them. I go and buy them because they're basically the old flash cubes that used to sit on top of cameras, instant cameras and whatnot. They had a little cube, and in that cube would basically, you hit the button and that one face of that cube would flash. And what that face was is it had a little bulb inside with basically sort of like a gunpowder type stuff that would make a nice bright white color. And the current going through it would set it off, and that would make a flash of light, and then that bulb would be burnt out. But mechanically, the bulb would turn 90 degrees so it could take the next shot. So I would take and buy those little cubes from eBay or wherever I can find them. And then I pull out one little bulb at a time by taking it apart, loosening the little wires. And then all I do is I take either alligator clips that are connected to the two ends of the wire and then attach them to the two ends of the light bulb, or I can solder it there or whatever. The main thing is you just have it there. And then through the center of that spool, you just drop a fairly powerful magnet. And lo and behold, that magnet shooting through that spool generates a magnetic field and therefore generates a flux that's changing. And as it changes, it creates an electric field that creates a current in the wire. That current then, of course, causes the flashlight to flash. So anything you have that can show a flashing by a current going through it, you could use. So for instance, you could use an LED. You just, of course, have to make sure you had it polarized the right way. And that's sort of what we're going to be talking about this time, is in which direction is the induced current going to go. Okay. Anybody have any questions about that? Okay, so let me start off with this. I'm going to go ahead and write out the main equation, the first part of the main equation anyways. And it's something that you're already familiar with, so we really don't have to show you any sort of examples with it. I mean, your book does some, but basically we're going to say the magnetic flux, which we give the same symbol as we did in the electric flux, but we subscript it B like that. That magnetic flux in its most generic form is the integral of B dotted with dA. Okay, so you imagine, you know, for instance, a surface like this. Maybe it has this little area bit right there. That would have a vector that's normal to that piece of surface. That vector is dA vector. The length of that vector is equal to the area in that little segment that it's attached to, but the direction of dA is, of course, perpendicular to that small surface. And if that small surface is not flat, then you'd have to choose a smaller surface until you get a flat part. And then, of course, you're going to dot product the magnetic field with it. So maybe a magnetic field comes through like this at that particular location. You take the dot product, that, of course, picks out the magnetic field component that is perpendicular to dA. Of course, that would be this component over here. So it only wants the part that, well, it actually picks out the part that's perpendicular to A, not perpendicular to DA. It picks out the part that B that's parallel to DA, which means this part right here. So it's the part that seems to go through that surface unslowed down or unaffectedly. Okay, so that's what the magnetic flux is. And of course, you'd integrate that over the whole surface, say. In doing so, you'd find out the total amount of flux, which you can see is a Tesla meter squared. And of course, there's another unit we use for the Tesla meter squared. And I want to remind myself of that. I should have. It's the Weber. Yeah, that's right. There's a bunch of different systems in a unit, so I always forget some of them, but this one's called the Weber. So 1 Tesla meter squared is the same thing as 1 Weber, which is a WB. Okay, these pictures are not that crisp. So here's a neat thing. If you imagine a little area in space where there's a magnetic field that's uniform and pointing out of the page, and let's say this area right here is called A1, and this area right here is called A2, okay? If you wanted to calculate the flux through there, through all of A2, the integral over A2 of B dot dA would actually be, this is a surface integral, which we've talked about before. This is a surface integral, and we're trying to take it over the entire surface area, A2. What you'll see is that basically there's no magnetic field except in this little area here. So it'd be 0 times, let's call the area A2 minus A, or excuse me, A2 minus A1. and then plus the magnetic field, which we said was B times A1. So it ultimately just be B times A1, because the area multiplied by the A is what matters, or excuse me, the magnetic field multiplied by the A is what matters, but anywhere the B is 0, it's not going to contribute. So that's a common misunderstanding that students have. So almost every book does something like this, just to remind you that, hey, the only part that matters is the part of the area that the magnetic field is actually penetrating. Any questions on that? So you can see, of course, in simple cases, this could be for instance, if the magnetic field is uniform, it could just be B dot A, right? Which we recognize as B times A times the cosine of the angle between them, where B is like that, A is like that, and theta is the small angle between them. Okay, so that's the simplified version, because you don't actually have to integrate all the times. The reason you have to integrate is if B changes from point to point to point, and the angle of DA changes from point to point to point, then you'd have to do the integrals and figure out, sort of a functional value of DA for each point in space and a functional value of B for each point in space. And then for each of those those points, you'd have to compute B dot DA for that and sum them all up. So this allows you the full freedom. This is in the special cases that you'll run into in a lot of problems. Okay. So your book gives you a couple highlighted terms. I want to go ahead and read those sentences to you. I've already given you a version that I like to use, but it says a current produced by an induced EMF moves in a direction so that the magnetic field created by that current opposes the original change in flux. So that's that same, it means the same thing as that sentence I said earlier, where I was saying that an induced current will be created in such a way that it opposes the change in flux. Notice it's opposing the change in flux, not the flux, and that'll make more sense in a second. But a current produced by an induced current EMF moves in a direction so that the magnetic field created by the current opposes the original change in flux. They also stated an induced EMF is always in a direction that opposes the original change in flux that caused it. Okay, so let me give you some examples. These examples are so important that I often use them as questions for people that we're hiring for a physics position. If someone's trying to teach physics at TCC or any other college I work at, I make a point to make sure I ask them some technical questions. And one of them that I frequently ask is about Lenz's law, because it really requires your understanding of physics. And even if you haven't done it in years, your understanding of physics will be shown even without the math. So here's an example. Let's look at a magnet, a bar magnet. This is the north end of the magnet. This is the south end of the magnet. And it's falling through a loop of wire. Okay. My question is, as this falls this way, which way will the current induced go? So in which direction does the induced current flow? So I'll say CCW as seen from above, or CW as seen from above. So those are our two choices. So if you look down this way, you can see this would be the front. In other words, that's the part that's sticking out of the page. and this is the back, which I'll write kind of barely, so it's like it's, you know, deep back in the page. Okay, so if it's going this way around, that's counterclockwise as seen from above. If it's going this way, that's clockwise as seen from above, which you can tell from my clock on my wrist that I'm not wearing. Just playing. All right, so anybody have a guess at this? Anybody have any ideas of how you're going to attack this problem? So if this, let's try this way. If this magnet is infinitely far away, would there be any flux through the loop?
No.
Exactly. So here's our reasoning. Magnet at infinity implies no flux through. And remember, what we're actually taking the flux through is a surface that the loop actually spans. So, and it actually technically could be any surface, but we usually just imagine a little flat surface if it's a little, you know, flat ring like this. So as it gets closer and closer, the magnetic flux gets bigger or smaller?
It'll get bigger.
Right.
It's going to go counterclockwise because the field, like if you do the right hand rule, and you point the magnetic field down, your index finger will go to the left.
I think you're on the right track. Let me work it. So what you're seeing is as this gets closer, the magnetic field is definitely starting to penetrate this disc, if you will. Okay. And remember, I taught you that magnetic fields are like old people. They leave the north and go in the south. Okay, so I got these magnetic field lines that are all of a sudden pushing this way, pushing down through the loop, right? Well, there was no flux. Now there is flux. So it tries to fight the creation of the flux. The flux that it's experiencing is a magnetic field through the middle. So it tries to decrease that by creating a magnetic field in the opposite direction. So how would I create a magnetic field upward with this ring? Do I have to use a clockwise or a counterclockwise? Induced current tries to reduce the flux by reducing B. Okay, so you see as it gets closer and closer, the magnetic field is penetrating this way. That it sees that as an increase in flux, so it tries to decrease the flux by creating a magnetic field that points that way. So how do I have to grab this wire so that the magnetic field in the middle is upward? Anybody? Do I grab the front with my thumb pointing this way? And this is what I think the student that answered was talking about. Or do I grab the front so that my thumb is pointing that way?
The first option.
I couldn't make it.
Thumb pointing to the right.
Yeah, when my thumb points to the right, you see my fingers come through the middle, come out and up. So yes, that would actually be considered counterclockwise as seen from above. So I'll call this B induced points up. Implies counterclockwise as seen from above. ASFA. I just made up an acronym. I like that one. ASFA. Okay, any questions on that? Does that make any sense? Now what's going to happen is this thing's going to fall all the way through here. And then at one point, it's going to have basically the maximum amount of magnetic field going through this. And then it's going to start to fall downward. So as the magnetic field falls through the middle, so I'm literally saying right now, let's consider when the center of the magnet is lined up with, well, on top of the plane, it's right there on that plane, and it falls down from there. What happens at that point? Is the flux increasing or decreasing? And then which way will the current flow? So now from magnet being centered in the loop to falling downward, which direction is I induced? Okay, so we're talking about the magnet's right here, dead center, and it starts to go out. So first thing we want to ask ourselves, one, is flux increasing or decreasing? So from the second part, where we've imagined the thing's already got to centered up on here, and then it continues to fall downward. So we're starting with the magnet in the center of this, the center of the magnet in the center of the ring. Is the flux now increasing or decreasing?
Decreasing.
It is decreasing. The reason why is it's basically got
It would
all.
be decreasing because the magnet.
What's that?
Well, would it be decreasing because the middle of the magnet bar is where the magnetic field is the strongest?
Yeah, it's most
So as
concentrated.
you pull it away from the center, it's going to get weaker.
Exactly. So remember, magnetic field lines never end. They go in complete loops. So the maximum amount that you can fit is right here. So they're going down at that point. And then as you start to slide down, these things become less dense packed and more of them are outside of the ring, if you will. So slowly the magnetic flux is decreasing. So the next question is, how does an induced current react to, or what does the I induced try to do? So does it try to increase or decrease the flux?
Increase the flux.
It's going to try to increase it. That's right. Okay. Three. Which direction will the the B induced point? Okay, so this is again that clockwise versus counterclockwise as seen from above. Or actually, no, since I'm talking about B, it's just up or down. Does the magnetic field have to point up or down to try to restore the flux, i.e. to increase the flux? So the flux is decreasing. we're trying to save the flux. So you always oppose the change in flux. The change happens to be that it's decreasing. So you're going to try to increase it. Now, the instant it was centered up, the magnetic field lines were pointing down through the center of the loop. And as it starts to fall, they're going to continue to point down through the loop, right? But they're getting farther and farther apart. So the magnetic flux is getting weaker and weaker. So we want to restore that. So which direction do I want my magnetic field to point? Up or down in the middle? My induced magnetic field.
It's going to point down in order to compensate for the loss.
Exactly. Down. And finally, what direction of I induced would cause that? What direction must I induced flow? So I want the current to go down, the magnetic field to point down now. So which way do I want the current to go? Do I want the current to go clockwise or counterclockwise? Or excuse me, clockwise, sorry, or counterclockwise, out to the right and front, and then to the back, in the back to the left. That's counterclockwise.
You can go clockwise. And
yeah, this way it's got to go clockwise, right? And the reason you know that is you want your fingers in the middle of the loop to point down. So you grab it with your right hand, that points down, you see your thumbs pointing to the left. So it's going to have to go clockwise. So I'll say CW as seen from above. Any questions on that?
this reminds me of the Doppler effect. Or,
yeah. Yeah, in some sense, that's you can sort of think of it as a conservation of energy. In fact, you could show that if the Lenz's law acted the opposite way, it would create a perpetual motion machine. So yeah, it's sort of like that, because one of the ways I use about thinking about frequency when I deal with a Doppler shift is think about how energy is going to be conserved. So yeah, I can see it bearing some responsibility or bearing some resemblance to that, if you will. All right, so what about this? Let's try another scenario. Let's imagine a uniform magnetic field. This time it's pointing into the page. And you have a loop of wire like this, perfect circle. And then you stretch it. In other words, you put your fingers inside and you pull it this way so that it shrinks this way and widens that way. So from full circle to oval is this increasing or decreasing? And what is the direction of I induced? Okay, so when I take this, initially we're looking at a perfect circle and we're stretching it into an oval. So did that cause a decrease or an increase in flux?
Decrease.
It's a decrease. The amount of magnetic field in general doesn't change, but the amount of area that is the magnetic field is going through has decreased because the area of this oval is smaller than the area of the circle. So yeah, it decreased. Been a long time since I wrote, and I'm finding myself writing half capital, half lowercase letters all the time. Okay, so since the flux is decreasing, we want to use Lenz's law to fight that change. So we're going to try to increase the flux. So which direction do I need the induced magnetic field to point?
Would it be upward? So the current's gonna go counterclockwise?
Not quite. You're off by like 90 degrees. Remember that these things represent the back of an arrow. So this means the magnetic field is going into the page. So that's what those red crosses mean. Now, anybody want to try it again? We established that it was, in fact, decreasing the magnetic flux. We're trying to increase the magnetic flux now. So we've got to try to restore the magnetic field that existed, right? Well, the magnetic field wasn't so much what changed, it was the area. But the thing is, we only have control over the current that goes in it, which can create a magnetic field. We can't change the area. All we can do is change the current, which creates a magnetic field. So, or create a current that changes or creates a magnetic field. So anybody want to say which direction the induced magnetic field should point? We're trying to restore it to greatness.
Clockwise.
You jump into the current, which may or may not be right. I'm not saying either way on that one, but you're talking more about current if you're talking about clockwise or counterclockwise. I want to know which direction the magnetic field has to point to increase the flux.
Would it be like it would have to go down? Go ahead.
I think I heard somebody say in. Is that what y'all said, or did y'all say out?
No, we said up or down, and yeah.
Now it's going to try to establish the magnetic field as it was. The magnetic field was pointing straight down through the page, through the middle. So it's actually going to point in. Now, the fact that you know the magnetic field induced is going to point in, which direction does the current actually flow to make that happen? Is it clockwise or is it counterclockwise? Remember, when you grab a wire, your thumb points it with the right hand, your thumb points in the direction of the current, your fingers curl around in the direction of the magnetic field. We want in the middle, we want a magnetic field going in.
The current would go clockwise then.
Yes. Yep. Just in case people are used to electronic watches, digital watches, as opposed to other ones, that means that way. Does that make sense? Now here's another one. Let's look at a slightly different problem. This time my magnetic field lines are going to be in the page, actually on the page, if you will, and all pointing that way above the page and below the page as well. But the main thing is they're parallel to the surface of the page. And initially, I have a wire loop like this. Okay, so there's my wire loop. If I looked from this angle, okay, what I would see is a loop of wires with what, let's say, magnetic field points coming out. It's supposed to be uniform, doesn't necessarily look it, but let's assume it's uniform. I'll put another one there. Okay, so that's what I'd see. If I'm looking this way, I'd just look at a loop. Now what I'm going to do is take that loop and rotate it about this axis right here. Okay, so that now that loop becomes at a slight angle. Okay, so A, did the flux increase are decrease, and B, which direction will be induced point, and C, which way will I induced flow. Okay, so y'all see what we had? We have a ring that's perpendicular to the magnetic field, but that ring starts to rotate this way. Okay, so it goes somewhere from here and comes close maybe to a 90-degree rotation, but not quite. So let's try answers. Is that going to cause a decrease in flux or an increase in flux?
Be a decrease in flux.
It will. Remember, the dA vector is going to be pointing straight out of the page like that. That means it's completely perpendicular to the page, but that means it's also completely parallel to the B. So B dot dA is just B times A. It's cosine of 0, in other words, which is 1. But as it rotates this way, B dot A becomes B dot A, or B times A times the cosine of the angle that it rotated through. So yes, it's going to decrease. So that means the flux decrease, the induced magnetic field is going to try to reestablish that by trying to make the magnetic field point through the loop the same way it was, but to make it stronger. So which way will the magnetic field have to be induced?
In the example from above would be counterclockwise.
Okay, so see how you're looking at it now. So with this one, this disc was like that. It's moving like that. Notice the magnetic field was pointing that way. As it goes like this, the magnetic field's got to point that way. And if I look from this way, that would be counterclockwise. Is that what you were meaning?
I believe so. I was looking at the example from where you look at it above, because
Yeah, the only thing was that
curve
was
your finger.
oppositely directed. That's what I was worried about, because these, the magnetic fields are going in, whereas these, the magnetic fields coming out.
Mm-hmm.
But yeah, I think you got it right. It's yeah, it should be counterclockwise as seen from left. CCW as seen from left. Or excuse me, that's right. I should learn my right from my left. That might be awesome, right?
And the way to think about it is that, I mean, it's just the right hand rule. If you wrap your fingers, like all 4 of your long fingers, in the direction of where the magnetic field is pointing,
right,
and then run that along the wire, your thumb will point on the current.
Exactly. So in this case, this is the side closest to us. So that current will be going, that way, and that would make the current going that way back behind. Okay, so I guess you got C now, which is the current will flow in the counterclockwise direction. This has to be out of ring from behind. So in other words, go behind the page, and it's going to try to still establish the magnetic fields popping out. So if my ring were like this, the magnetic field would point coming out like this point right here. Okay, so that's sort of the tough conceptual problems with ultimately what's called Faraday's law. And like I said, we often use the magnetic or the negative sign in the actual equation. We normally indicate that as Lenz's law. So let me go ahead and state Faraday's law so you'll know what it is. But basically what we found out is that you can actually do a couple things. You can actually realize that the flux, which is B dot dA, induces a electromotive force. So the induced electromotive force is E is equal to negative d phi b over dt. Okay, so there's our magnetic flux. We got to take the time derivative, and this negative is often what we're referring to when we say Lenz's law. But this whole thing is Faraday's law. And it was really cool. He actually had to use like a sort of a liquid metal of like mercury to get this to happen. So he could see that it was actually would work this way, but it was pretty brilliant experiment for him to come up with. And he did find that it only did it when it moved. And that's Lenz's law. You can actually get it by recognizing that E is equal to the integral of E dot dL. And then that equals negative d by dt of the integral of B dot dA. So that's sort of the long integrated form of it, but you can do certain mathematical tricks that allow you to reduce it to that. So that's it. And that's kind of nice because we recognize if you have, for instance, let's say you have this long wire like this that's in the shape of a U. And let's say you have a bunch of magnetic field lines coming out of the page, but uniformly distributed, of course. So that way V is a constant everywhere. Let's maybe even add another row, or column, I should say. Now, if you happen to have a metal rod across this, that's moving so that it initially was at x0, and now it's at x of t. I wrote that really small. Now it's at x of t. Then your flux, if you call this length, let's say L, from here to here, since the magnetic field is actually uniform, then we don't have to do B dot dA and do all the integrals. And we already see that B and A are parallel. The surface area vector would point parallel to that. So we're just going to have B times A, but the A would actually be L times basically X of T. So you get a flux as a function of time. And in fact, you could say it went, you could say that X of T is equal to V T plus X0. Meaning it was right here initially. And then after some time T, it went additional distance V times T. And what you get now is V times L times X0 plus VT. And when you do that math, it comes out actually quite easy. It's B times L times V. well, you should put the negative in there, but whenever we're talking magnitudes, we just drop that negative, because that, I always think of that negative as just something to remind me of Lenz's law. The main thing is you now have to be able to tell me not only calculate the magnitude of the induced voltage. Remember, induced EMF literally means voltage. Okay, so this has units of volts. So that voltage is equal to the magnetic field strength times the width of that times the velocity. And if you actually were to say, want to find out the current going through it, all you have to do is find out the resistivity of this metal and this metal. And then, of course, use V equals IR. So you can say that's equal to IR, and you can get the current going through it as well. So any questions on that? This is an expression you're allowed to use. I think your book even took the time to number it. Let's double check. Yes, they call it equation 29.3. So that means that's one that you can put on your equation sheet, and you can use that way. Now, the more general form of Faraday's law doesn't have to be held to just one loop of wire like we've been talking about. In fact, you can also do it like this. You can say E is equal to negative N d phi B over dt. Because in that case, that's when you have, instead of a single loop of wire, you actually have N loops of wire. So both of these are fair game. Obviously, when you only have one loop, you only need this equation, but when you have 20 loops, you have that. So if you think about this, this is not that much unlike an airplane flying through our magnetic field. So an airplane literally is like this rod right here. It doesn't have these parts to complete the loop, but the fact that that rod being there creates a current that'll flow around either this way or that way, that tells you that, yeah, there's going to be a voltage difference between this end of the wing and this end of the wing. And that voltage, maybe that's a big voltage, maybe it's a small voltage. Your book actually has an example for you to work on that, because you're just going to use B, the strength of the magnetic field, which is 1/10,000th, or excuse me, I think a half of a 10,000th of a Tesla. The length of the wings, which obviously the bigger that is, the bigger the voltage, and then the velocity of the aircraft. So you can actually calculate that again without the negative, and that would tell you the voltage difference. But now that we're looking at this and we see that the bar was initially here and it moved that way, is the flux increasing or decreasing?
Would it be increasing?
It is increasing, yes. Okay, so that means the Faraday's law is going to cause the induced current to try to oppose that increasing flux. It's going to try to decrease the flux. So it's going to create a magnetic field pointing what? Into the page, out of the page, clockwise, counterclockwise, what? Magnetic field we're talking here, not current.
It'd be into the page.
Yes. Because it's trying to decrease the flux. Currently, the flux has a magnetic field pointing out of the page, so it's going to try to go into the page. And I induce, therefore, which has to be which direction? Into the page, out of the page, clockwise, counterclockwise.
It'd be clockwise, I think, in this example.
Yes. Yeah, because if I grab this piece of wire right here with my right hand, I can see that my finger is going to point down in the middle and my thumb is pointing to the left. So that means it's going to go this way, this way, this way, this way, and that's clockwise. So good job. So that's a neat little equation that you can make use of, obviously, whenever a bar like this is moving. But it, you know, don't be surprised if I ask you not only for the magnitude, but I ask you for which direction the induced voltage will be. And not only that, I can ask you, or excuse me, which way the induced current will be. And that of course means current flows in the direction of decreasing voltage. So that's fair game too. But you can also use now, since V is equal to IR and E is essentially the same thing as V, then you can also compute that I is equal to BLV over R. So that's another expression you can make use of. This time I wrote it without the negative just to alleviate some confusion. So didn't really do much as far as specific examples, computing with numbers and stuff like that. But the main thing is I needed you to understand how all the different ways this equation can be used. We can now use, for instance, since we found out how a force is applied to a current carrying wire when the current carrying wire is in a magnetic field, remember that F equals Bill equation? We can use that in conjunction with this to say things like, well, how much force does it take to pull that bar through the magnetic field? Does it automatically want to move on its own, or does it require some force? So let's look at that. Let's imagine I'm going to do a magnetic field. This time I'm going to do it into the page. So here's an X, here's an X, here's an X. Okay, and now I'm going to have a chunk of wire come around this way, go out this way like this, and I'm going to move a rod this way with velocity V. And this length right here is going to be L, like I did before. And what I want to do is I want to make the rod move at a constant speed, and I'm going to apply force to it to make it do it. And what I want to do is determine the magnitude of that force, and then maybe think about the amount of power and therefore energy has been created, so we can even compare that. So let's first talk about the force. What we know is F equals I dl cross B. You guys remember that? That was the equation that we used. Of course, I didn't write a fancy F like that time, but that's what happens when you go to write an F, an I when you meant to write an F. So we had that. In this case, the DL, in all cases, DL is supposed to be parallel to the current. This is a straight current carrying shaft, if you will. So IDL is just pointing in the direction that the current goes, which we can imagine, say, is going this way. I haven't worked that out, but we can work that out. And then the cross B, the B is uniform. It's pointing in the same direction, doesn't change over time. So all this just becomes F equals B times I times L, where L is the length of that wire. Okay. Now it's actually the length of the wire that carries the current. So it's actually sort of leaving off that little nub at each end. But what I got to figure out is, okay, well, what is that current? Well, what I know is that the induced EMF is equal to B times L times V, right? So I can now say that F is equal to B times L times V times L. So I'm going to get that the force is B squared L squared V. Now, that is actually what the EMF is. Oh, scrap, I completely. So I, R is equal to E gives me that basically I would be E over R. So I actually got to include that resistance down here. Sorry about that, everybody. Yeah, I jumped ahead of myself. So basically I set this equal to IR, and to solve for I, divide both sides by R. So I got BLV over R. So this became B squared L squared V over R. and that's ultimately the force required. So F is equal to B squared L squared V over R. That's the force required to push it. Now let's think about that direction. What we have is we have a magnetic field pointing into the page. The flux, because the rod is moving this way, the flux is, anyone, increasing or decreasing?
Increasing.
Yes. So the flux is increasing. That means the induced magnetic field is going to point what way?
Out of the page.
Yes. Because it was increasing, it's going to try to decrease. So it's going to try to cancel out that magnetic field, which means it's going to point out of the page. Which means I induced is going to be what? Clockwise or counterclockwise?
Counterclockwise.
Yep. Good job. Okay, so we now know that the current's counterclockwise. That means it's going this way. And we have I, DL would point that way. Cross with B would be that way. So yeah, the force is actually trying to pull it back in. So what we're doing is computing the force required to pull it out. So in other words, it would naturally slow it down if you just tried to sling that wire out. If you try to sling that shaft out, maybe it's sitting on wheels or something like that, it would actually try to pull it back. It would slow it down over time. So we've decided that. So implies we have to apply force to the right. So that's how we worked out all that. That's nice, right? Now what we want to do is say, what external power is needed to move the rod? So in other words, what kind of, power would we have to take? Power is nice because that's energy per time, which if we're dealing with current, we already have a per time. So power is equal to work divided by time. That's the normal way we think about it. And work is equal to F times F dot dx. Remember, work equals the integral of F dot dx, right? Now this force is going to be that way and the displacement is going to be that way. So it's just F times the dx. So when you say power is equal to F dot dx over dt, you look at it in infinitesimal time, you'll see that power is equal to F times V. So we already found that the F is B squared L squared over times V over R. So the power is equal to B squared L squared V squared over R. And if you wanted to know how much energy you put in, well, basically you could say multiply this times the amount of time it took. That would work it out. But either way, that's kind of interesting that you can calculate that. So those are two expressions. I don't think your book numbered those. No, they didn't. So if I ask you that kind of problem, you're going to have to show me the work to get to it. In other words, you can't have it on your equation sheet. So any questions about that example? All right, so here's where we can start to make sense of things like alternators and steam turbines, stuff that we use to generate electricity. And this, of course, is where Tesla came in. Edison was trying to power New York, as was Westinghouse, as was later on Tesla, of course. But Tesla first started working with Edison. Edison, there's some question as to whether Edison really understood AC that well, or whether he understood it. He just was, greedy and didn't really care. He just wanted to make sure, he got a ton of money out of it. We're not sure, but at the end of the day, basically Edison, for some reason, fought for DC, and Tesla was with Westinghouse by that time, and Westinghouse was fighting for AC because of what he learned from Tesla. And I even told you the horrible story about Edison blowing up an elephant to prove the dangers of AC, even though you could have done exactly the same thing with DC. You just have to use, that much power, but in a DC variety. But anyways, ultimately, luckily we won. And the main reason we win is because it's so easy to step up voltage from low voltage to high voltage, and then step it back down from high voltage to low voltage. And because of that, we can make use of the fact that P equals I squared R. If we send a buttload of current, 200 miles across the country to neighborhood from a power generation factory, like say a dam or a nuclear power plant or whatever, we're sort of locked in to however many houses we're serving. So if you had, for instance, 10,000 houses, each house gets 200 amp service. That's generally what houses use. So this is going to be fixed. That's a fixed amount of current that you have to blow through there. As you can tell, though, 10,000 houses times 200 is quite a lot. And then you're going to square that, and that's going to be power that's lost. But because magnetic flux is equal to magnetic flux, it turns out that you can actually do N, basically the number of turns, times phi 1 is equal to N2 times phi 2. And in other words, that phi being directly related to E, you can actually change the amount of voltage coming out as long as you change the number of coils in two ends of, say, a bar magnet. So you could have, for instance, a bar magnet like this, and you could have, say, 10 turns here, and you could have, say, 1,000 turns here. What's happened now is you've increased the voltage from 10 volts to 1,000 volts, but you've decreased the current from whatever you had to that divided by 1,000. So you can actually, by bumping that voltage to a higher voltage, you're decreasing the current by the same amount, and therefore you're getting rid of this loss of energy. So that's ultimately what won it out. Of course, Tesla's the reason that we have our 60 hertz electricity here in the United States. I think Great Britain uses like 45 or something like that. That's one of the reasons why stuff gets burned up. You have to get an adapter if you're taking any electronic devices or plug-in devices and you go to Europe. Their electricity is different. So how does all that work? Well, you've learned a little bit about what happens for as inducing current. So you imagine if you took a wire like this, and I'm trying to show 3 dimensions on a 2-dimensional sheet of paper here. So this is actually a flat loop of wire at an angle with respect to the page. So it's somewhere between right here and right here. Okay, that would be flat on the page, that would be perpendicular to the page. It's at like a 45-degree angle. Now, if you're fortunate enough to make a really strong magnetic field, and say this is the north end of the magnet, and over here is the south end of a magnet, and you use a very, very strong magnet, then what you know is if this thing rotates about this axis, so this is like a little axle here, if this thing rotates, then it's going to induce a current in here, and during one half of a cycle, it's going to induce it in this direction, and then the next half of the cycle, it's going to induce it in that direction. So you ultimately get out a current versus time that looks like this. Where basically these peaks are where the A vector, which is perpendicular to the loop, is actually parallel to the magnetic field, or anti-parallel to the magnetic field down here. So we end up getting I is equal to some I0 times sine omega t, where omega is equal to 2 pi times the frequency, and the frequency for us is 60 hertz. Okay, that's how we generate electricity. Now, the problem is one little loop ain't going to give us that much, but we can take that loop and wrap it n times, and then we'd have n times as much current, because E is equal to negative n d phi dt. So if you actually had that phi is equal to B times A times the cosine of omega t, then the B and A are going to be a constant. What's really changing is that angle theta that B makes with A. And of course, you'd get derivative of cosine is equal to negative sine. So it's be positive n B A omega sine omega t. Because the chain rule requires us to take the derivative of cosine with respect to the argument times the derivative of the argument with respect to t. So that's why I got the omega out there. So that's going to give me my voltage. And of course, if I took that and divided it by the resistance, I'd get the current. So current would equal N BA over R omega sine omega t, which is what I was showing you here. So obviously this would be I0 would be N times B times A over R. Okay. Now, of course, you can think that the tricky part would be, how do I, get that electricity out, because it's spinning and stuff like that, where they have stators and things like that. So they have ways where this wire can sort of run on that, but it can still touch and deliver a current. So your book talks a little bit about that. That's a useful thing to have. But that's generally how all AC power is created. It's just a matter of what's making it spin. So you could, for instance, have a propeller. So if you allowed water to stop at a dam, and then you drilled a hole through the dam, and then put a propeller in that hole, water brushing through it would cause that propeller to spin, and that would actually make this spin, and that would create electricity. Another way they do it is they put it over a boiling vat of water. So you can take either take natural gas or coal or nuclear power plants and boil water. And by boiling water, that's going to cause these propeller blades to spin. And that's what a steam turbine is. Of course, the propeller is much more complicated than that and stuff. But still, by running it through that, you get our most efficient energy conversion method. So basically, we're getting energy conservation. We have to waste some energy. That's just the laws of physics. But people like GE and Philips and other really large companies have worked for these for decades, trying to figure out the most efficient way to convert heat energy into electrical energy. And therefore, we have power plants that are super efficient at converting this heat energy into electrical energy. Same thing with a windmill. You can do it with that. But with the given problems that we have with global warming, or more specifically what we call global climate change, because we had to reel that term back, because people would say, oh, well, it snowed really hard, so that can't be global warming, or that global warming can't be real. So stupid stuff like that. Basically, global warming suggests that the average temperature of the globe, in some sense, is going to be increasing, and because of that, that actually makes winter storms more severe, because they have more energy absorbed in the atmosphere because of its warmth, and summer storms will be more severe as well. So it's perfectly normal to have, in fact, more blizzards in global warming than you'd have in a non-global warming situation. But anyways, because of that, we're trying to get away from fossil fuels. And any fuel really that has carbon in it, because when you release 1 pound of carbon, the compound is carbon dioxide. Carbon weighs about 12 grams per mole. Oxygen weighs about 8 grams per mole, and you have to have 2 of them, so that's 16 grams per mole. So for every 12 pounds of carbon you're actually creating 12 plus 16 or 28 pounds of CO2. So ideally, we'd like to go to, say, really safe nuclear or solar or geothermal or tidal energy production, that sort of thing, but all of them would use some kind of steam turbine or some kind of turbine like this. Any questions on that? Your book also talks about an alternator. It has a really nice picture of an alternator that they took a long time to to draw. And that's nice just so you understand how your alternator works. Your car is not supposed to be running on its batteries at night. It's when you're driving at night or when you're driving at day. It's actually supposed to be running off the electricity through your alternator, but the alternator is also charging the battery. So now the last equation for this is really our transformer equation. And basically what you look at is you can imagine a power source. It's an AC source coming in called VP, and that means primary. Okay, so this is a power source coming in, and you've got to, of course, have a way for the power to come in or for the current to come in, and then a way for the current to go back out. So I always tell my students to imagine the old-timey pilgrim belt buckle. You know, whenever you do your Thanksgiving Day parade sort of thing, somebody's wearing one of these cheesy belt buckles. Well, you take that iron belt buckle and you send a current running through here that's at a voltage VP, and we'll have a number of turns in primary here. And then on the other side, we'll have a number of turns in S, which I tried to make obviously a lot bigger, and out will come a current at a voltage of V secondary. I don't know why I wrote it in there, VS. Well, we know, for instance, that VS is equal to NS times d phi S over dt. And we know that V primary is equal to N primary times d phi primary over dt. Now, we make this out of iron because iron holds the magnetic field inside it very well. And we even, they'll even take and make it in fine little plates and bond them all together and stuff, specifically so you don't get a bunch of eddy currents losing your energy. Not only that, you'll put them in liquids that help it make it harder for the magnetic field to escape it. So they'll put it in carcinogenic oils and stuff like that and make a really, really efficient one. So if it's absolutely 100% efficient, which it's not, but it's close. But if it is, then you'd get d phi p over dt is equal to d phi s over dt. So what you see is V primary over N primary is equal to V secondary over N secondary. So if you looked at V secondary would be N secondary over N primary times V primary. So if N secondary really is bigger than N primary, then you've got like 100 over 10. So that's actually going to make the secondary voltage larger. So NS greater than NP means a step up transformer. Okay, if it's the other way around, it's a step down transformer. And they always talk about that with regards to the voltage, not with regards to the current. Now, it turns out, as you know, V is equal to IR. So V and I are actually sort of play opposite roles. So what you see is that I secondary over I primary is equal to N primary over N secondary. So in this case, if you actually wanted to solve for the secondary, I secondary would be equal to NP. Oops, made that too big. NP over NS times IP. So this steps down I when NS is greater than NP. So by changing the voltage from typical from a power plant, I think might be on the order of 10,000 or 20,000 volts, something like that. They'll step it up to 200,000 or even 1 million. But if it was 2,000, they stepped it up to 2 million, that would be 1,000 times as many turns here as there are here. That means the current's going to go down by a factor of 1,000, and that means the P squared, P equals I squared R is going to be reduced by a factor of 1,000,000. So it saves them a buttload of money. So these are your transformer equations. And that's basically it for this whole chapter. There's not really much else to talk about. I've already given you the E dot dl equals negative d phi dt. Oh, I will probably work example 2914. Actually, that's on my page. See example 2914 and see it on my YouTube channel. I don't have enough time to show you now because time's up, but I might show it to you next time, but definitely look for it on my YouTube channel as well as read it in the example. But basically you have something that is a lot like Ampere's law, which we just discovered, which we just taught you. That is the closed integral of E dot dl instead of B dot dl. Remember, Ampere's law was the closed integral of B dot dl equals mu 0 I enclosed. Well, this one's going to be equals d phi over dt. So if you can think of d phi dt as like a current, then you can create a magnetic field that's going to go in a circle. Electric field that's going to go in a circle. And you do it just like Ampere's law, except now you're calculating an electric field instead of a magnetic field. So that's it. You folks are free to go. I'll wait for the last person to leave in case you have any questions.
Have a good night, Professor.
You too. Don't forget to get your test done by Sunday. Alexi, Gavin, Jacqueline, y'all still there? Have any questions you want to chat?
Yeah. I was just writing the last two equations.
Okay, no problem. Yeah, it was out of the screen when I was talking about it, and I didn't realize it until after it's too late.
Yeah.
Yeah, remember this from Ampere's law, where you basically make an Amperian loop around the coil of around a current carrying wire, and you'd make the assumption that the magnetic field was parallel to that little Amperian loop. And this one, you're going to do the same thing. You're going to make the assumption that E is parallel to a little Amperian loop, but the magnetic flux, the derivative of that, is sort of going through the middle, and that would create a electric field lines that go in circles, just like magnetic fields do. So
all right, I got those written down, so I'm gonna head out. Thank you.
All right, have a good one.
Yeah, have a good one too.